Hi folks, today we're going to go over the 85s. There are some things that you definitely need to have out. So these are the things you need to get out. Pause the video if you need to go and get those items so you're ready to go. We're not going to worry about the belt work at this moment. All right, so we first need to make sure that you know how to measure. This is not on your sheet, but we're going to go through it anyways. So what does each line count for on this graduated cylinder? Pause the video, see if you can come up with an answer. Each line on this graduated cylinder is 0.1 or a tenth of a milliliter. So the measuring rule states that you should read an instrument one place value less than what each value is worth. So if we have each line worth a tenth, then we should read it to 100. We really don't need to follow that rule if we just learn how to measure correctly. So here we have 3. We know our measurement is exactly, or at least, 3 milliliters. This is 3.1, 0.2, 0.3. So this is the 0.3 line, and this next line is the 0.4 line. So we know that this meniscus right here is between the 0.3 and the 0.4 line. So it's 3.3. We feel very confident on those numbers. Now we have to estimate just a little bit further. So the bottom of the meniscus is what we read to. So the very bottom of that curvature is what we read to. I say it's greater than halfway. So it's a little bit more than halfway. I would not want to put a 5 there because I don't think it's exactly halfway. I'm probably going to go with a 7 on this one. And the 7 is my estimate. Could it be a 6? It could be a 6. Could it be an 8? It's a possibility, but that last digit's always an estimate. And that means that last digit can go up by 1, maybe up to an 8, could go down by 1, could go down to a 6. But either way, that last digit is our estimate. So we are 100% positive of the 3. We're 100% positive of that 3. And this last digit is an estimate by the person that's doing the measuring, and it is part of our measurement. And as always, put a label on it. So it's considered a significant number to our measurement. Go ahead and try to get the measurement on this one. Pause the video, do the work. I do believe that that meniscus is right on that 3 line. I put a 3 down. I feel very positive of that. I don't think that meniscus is below that 3 line at all. I'm going to go 3.0. So now, if I look at this, this digit could go up to a 1, so 3.1. This digit could go down to a 2.9. Is it a 2.9? It's not below that line at all. So I don't believe it is a 2.9. So I'm going to go 1 more digit, go into the hundreds place. Since each line goes up to the tenths, I should measure to the hundredths. And what that says is I am positive of that 3. I am positive of that 0. And my last digit is what could fluctuate. Could it be a 1? It is possible that it could be a 1. Could it go down and be a 9? It is possible. So my measurements here could be 3.01 at the greatest. I do believe it is 3.00. It could go down to 2.99. This last digit is an estimate. It is part of my measurement, and it is a significant digit or a significant number in our measurement. And of course, I put a label of milliliters on it. If in this case, all I did is put down 3 for an answer. So let's say I thought the measurement was exactly 3, and I stopped there. That last digit is my 3, and it means it could go up by a digit up to a 4, which means the meniscus would be way up here. That's not true. It could go down to a 2, which means the meniscus is down here. That's not true. So that's why going a 0, saying it's right on that line. This could go up by 1, which means it could go up to 3.1. Oh, it's not 3.1. It could go down to 2.9. That's right there. Oh, it's not down at 2.9. So that's why throwing that extra 0 at the end really does clarify that the meniscus is right there. All right, go ahead and measure the centimeter ruler. Measure as if we're going from 0 all the way out to where the tip of that arrow is pointing. I look at this one. I know that arrow is past the 14 mark. I feel 100% positive of that. Each of these lines is 0.1 centimeters. So this is the 0.1, this is the 0.2, and this is the 0.3. So I'm going to say it's point, and it's not to the 0.3 yet, so it's a 0.2. I feel 100% positive of those three numbers. Now, we've learned measuring in other classes, and in chemistry, we're going to be a little bit more accurate with our measurements. So what we say is if the last digit's a 9, it is so close to that line that we could accidentally think it was right on that line. But I look at that, I see the tip of that arrow, and I'm like, I know that's off that line immediately. So that means the last digit's not a 9. It's pretty close, but that means that last digit's probably an 8. So a 9 means it's really close to the line. You could barely tell, maybe 9 out of 10 times you'll make the mistake and think it's right on that line. If you can look at it right away and see it is off that line, it's not a 9. Same thing goes for a 1. So let's say we're going to go, the tip of the arrow was right there. So 14.6. And if you have to look so carefully at it that, maybe you think it's right on that line, it looks almost right on that line, but you know it's not, then it's probably a 1. If you can tell immediately it's not on this line right here, then it's probably a 2. That's kind of the difference when you're using those measurements. And of course, we would throw a label of centimeters on this. The last digit is significant to our answer. Going back to our initial, this could go up to a 9, this could go down to a 7. There's our estimated digit, and those would be accepted answers. So the last digit in any measurement is an estimate and can fluctuate up or down by usually 1 digit. Therefore, it is part of the measurement and is a significant digit. True or false? Brazen, Reed, and Scheidler are 6 feet tall. Take a guess. True or false? True. We all fall between 5 and 7 feet. Remember, the last digit in any measurement is an estimate, and it can fluctuate up or down by 1. True or false? Brazen, Reed, and Scheidler are 6'1" tall. Well, the last digit can swing up or down, so that means we're all between 6'2" and 6'0". Well, that's not true. They might want to be 6 feet tall, and they can be 6 feet tall, but there's no way they can be 6'1" tall. Find the front cover of your unit pack. Pause the video if you need to go find it. The back side of the cover has some rules and examples of everything that we're going to cover today. As you work, have these rules out, read them until these rules really are ingrained in your head. So here are the rules that are on the back of your front cover as far as significant digits go. All non-zero digits are significant. So in other words, any numbers 1 through 9 are considered significant. Number 2, all zeros between non-zero digits are significant. Zeros that are trapped between non-zeros are significant, like 103. That 0 is significant. Zeros to the right of the last non-zero are significant if there's a decimal point somewhere in the number. So 2.50, that's what we're talking about. That 0 is significant. That is part of our measurement, and therefore it is significant. That's what this says right here. Those zeros are part of the measurement. If they were not there, the numbers before them could vary up or down. So number 3 is all about measuring. Those zeros at the end are part of our measurements. They are significant. 4, zeros to the right of the last non-zero are not significant. So this 200 only has 1 sig fig. These zeros are not significant because there's no decimal point there. There's a decimal point like this right here, though, those zeros do become significant. Placeholder zeros are not significant. What do we mean by that? So no decimal point there. These zeros their only job is to push this 200 out. Those are called placeholder zeros, and therefore they're not considered significant. It'll take some time to learn these. All of the confusion comes around 0. And 5, all zeros to the left of the first non-zero are not significant. So in this example, we're looking at this. These zeros' job are simply to push that 2 over. So again, those are called placeholder zeros, and they are not considered to be significant. If you can take a number and write it in scientific notation. So if we look right here, we got the top number, and then this bottom number is in scientific notation. Those first 3 zeros disappear, therefore they're not significant. So if we look here, it shows you the number of sig figs. It shows you the rule that we're dealing with. So we got 5 sig figs. Here we have, oh, I got to fix this for you guys. Those should have 3 sig figs each, 3 sig figs each, 4 sig figs as we're looking through those, 3, 2. If I put a decimal point there, all of a sudden I'd have 4. And then down here, 2, 2, 2. Those are all examples of having 2 sig figs. And then this has 2 sig figs, and this has 2 sig figs. So look at those examples often. Again, I apologize for right there. I got to fix that one right there. That should be a 3 sig fig. Rules are stated right there if you need to look at them. Eventually, this will all stick in your head, and all will be good. So significant figures to 85s. So how many significant digits are in these numbers? What does your gut tell you? Well, 2 sig figs, 3 sig figs, 4 sig figs. All non-zero digits are significant. Why don't you try this one? Pause the video, give it a shot. How many sig figs do you think are in each of these? Well, these are trapped zeros. So this is 3 sig figs. This is 4 sig figs. This is 5 sig figs. Zeros that are trapped between non-zeros are significant. Again, pause the video, give this a shot. If this 0 is not here, that means this 3 could be a 4, this 3 could be a 2. But the person that did the measuring said, no, it's not 1.2, it's not 1.4, it's exactly 1.3. So that's where the 0 comes in and makes it very important to the measurement, because that 0 becomes our estimated digit. Therefore, this number has 3 sig figs. Same thing going to the next one. This 0 means that this 2 is an absolute correct number. If this 0 was not here, if these zeros were not here, this could be a 3, this could be a 1. But the person that did the measuring said, oh no, it is exactly 9.2. And it's exactly 9.20, and that's where this second 0 comes in. So this instrument has a great degree of precision. It goes to the thousandths place, and we would not want to chop off that 0. So in this problem, we do have 4 sigs, and those zeros are considered significant. And in this case, this decimal point has these zeros trapped between it, so this is a 5 sig fig number. Zeros to the right of the last non-zero are significant. Zeros to the right of the last non-zero. So zeros to the right of the last non-zero are significant if there's a decimal point. Zeros that are showing precision of an instrument are considered significant. So in other words, following the measuring rule. All right, count the significant digits. Go ahead and give it a shot. Use your unit pack cover if you need to. This one does have 2 sig figs. This one does have 2 sig figs. This one does have 4 sig figs. So let's talk about that. If I put a decimal point there, they all become significant. But in the olden days, they didn't always want to write in scientific notation. So this number with the decimal point not being there is a way of writing a 2 sig fig number. Because I could write this as 2.3 times 10, and I have to move it 1 spot, 2 spots, 3 spots. I could write the number like that. But if you didn't want to write it in scientific notation, they had this methodology where we don't have to write it in scientific notation, still can only have 2 sig figs. So if I put a decimal point there, boom, they all becomes significant. But as it's written originally, this only has 2 sig figs. Let's go to this very last one over here. These zeros are trapped between non-zeros, so they are significant. So our 4 significant digits in this problem are these right here. I could write this as 1.005 times 10. Then I'd have to go 1, 2, 3, 4, 5 spots, milliliters. And these zeros disappear when written in scientific notation. That means they're not significant. In all these cases, though, if I simply put a decimal point there, all those zeros become significant. Count the sig figs in this one. Give it a shot. Pause the video. This one has 1. This one has 3. This one has 3. So let's talk about that. The job of these zeros are to simply push the 6 over. They're considered placeholder zeros. Therefore, they're not significant. If you can write a number in scientific notation, 6 times 10 to the 1, 2, 3. And since this number is smaller than 1, it's a negative exponent. If you can write it in scientific notation and the zeros disappear, those zeros are not significant. So those are not significant zeros. Let's go to the next one. This 0 shows the degree of precision in which the instrument was read to. If that 0 was not there, this could be a 6, this could be a 4. But the person that did the measuring said, no, it is exactly a 5, and that's where that 0 comes in. So that 0 is part of the measurement and therefore is significant. These zeros, all they are simply doing is pushing that 350 over. They are placeholder zeros, therefore they're not considered significant. And if you can write the number in scientific notation, and the zeros disappear, they are not significant. So in this place, I'd have to go 1, 2, 3, 4 spots. That's where the 4 comes from. This number is smaller than 1, so I get a negative exponent, and I would put grams behind it. This 0 is so insignificant that most of you don't even place it into your calculator. But I could write this number as 5.66 times 10. And this number is smaller than 1, so negative 1 gallons. And the 0 disappears. So what is the rule? All zeros to the left of the first non-zero. All zeros to the left of the first non-zero are not significant. I like to call them placeholder zeros are not significant. If the number can be written in scientific notation and the zeros disappear, the zeros were not significant. So 3 different ways to know that rule. Now we got to talk about degree of precision. What is the least precise number in each of these pairings? Which number has the least degree of precision? So I look at this first one right here. This is the first one I'll take on. This one goes to the hundredths place, where this one goes to the thousandths place. This is my least precise number. It only goes to a certain degree of precision. That precision is the hundredths place. Where this one over here goes to the thousandths, it's a more precise number. You go through the other 4 and circle the one that you think is the least precise. Pause the video and do that now. Well, hopefully you did that. So this is my least precise number in this one. And if I go to this next one over here, this one goes to the ones place, so that's my least precise number. And if I go to the next one, this one goes to the tens place, where this one goes to the ones place because of the decimal. So this is my least precise number. I go to this bottom one for temperature. This one goes to the ones place, where this one, there's no decimal in it, so it goes to the hundreds place. This is my least precise number. And I go to the last one, and this one goes to the hundredths place. This one goes to the thousandths place. This is my least precise number. Now, the addition rule talks about precision. Your answer can be no more precise than your least precise piece of data. So if I go to this original problem that we're working on, this one right here, my answer can only be as precise as my least precise piece of data. So in other words, this one only goes to the hundredths place, so my answer could only go to the hundredths place. I could not give an answer that goes to the thousandths place. I go to the next one. My data precision goes to the ones place. So if my data precision goes to the ones place, and I was going to do some addition here, some subtraction, my answer can only go to the ones place. Why don't you do the next three? Pause the video and do so. In this next one, the degree of precision is the tens place. So my answer would have to go to the tens place. This one, my answer goes to the hundreds place. So my precision can go to the hundreds place. So in other words, if I gave an answer, I could only go to the hundreds place. And in this last one, I would go to the hundredths place. Major reason why significant digits, significant figures are important is to not pass along data that is more precise than was actually measured. Many times our calculators spit out all kinds of numbers to us, and it makes it seem like we have a great degree of precision when we're doing the work, but we really don't. And that's just because our calculators are spitting out all kinds of numbers to us. Remember that the last digit in any measurement is an estimate and can vary up or down by the number of 1. Many times we'll get numbers like this on our calculator. And if we were to pass that number on, the person would think, holy crap, they were using some really awesome equipment because their measurement went to the trillionths place. Well, folks, most of our equipment, if we're lucky, goes to that hundredths place at most. So a lot of times our calculators will give us impossible numbers, saying that we used impossible precision that we did not use in class. So make sure we're not passing on numbers that have so many digits, and that's what significant digits do for us. Make sure we only pass on the data that we can be sure of. So we're going to work on 85.1, and we're going to reveal some answers as we go on along. You need to realize that there are some answers at the bottom of these pages that assist you as you're working. So it says, when is a 0 not counted as a significant digit? If you can't find the words to the answer, use some examples. So placeholder zeros are not significant. So these are two examples. All they do is simply push that 2 over their placeholder zeros. You can write it in scientific notation, times 10 to the 1, 2, 3, negative third, and therefore those zeros are not significant. These zeros, all they do is they push that 1 over their placeholder zeros, therefore they're not significant. And you could write this as 1 times 10 to the 1, 2, 3. So go ahead, give these problems a try. Keep checking back in with the video and see if you got them correct or not. So number 2, these are all significant digits because there's no zero, so that's an easy one. Any number written in scientific notation will be considered significant. So these are all my 3 significant digits. I don't look at these at all. I just look at the digits in front of the times 10. I don't worry about saying, okay, this is really 5340000000000. I don't care about that. I don't look at that. This number was written in scientific notation. I'm asked to find the sig figs in this number only. I do not look at the actual number as it's written out. This has 3 sig figs, so that's why that answer is 3. I don't look at this times 10. I don't consider the 10 a sig fig. I don't consider the 15 sig figs. I just look at the 5, 3, 4. The 0 is not significant, therefore it's not counted. Again, we don't even put that into our calculator, so we really wouldn't want to count that as a significant digit. This 0 is trapped between non-zeros, so it's considered a significant digit, so we count those all. 6 and 7, these zeros are trapped between non-zeros, so they are counted. Same thing with this 0, trapped between non-zeros, so it is counted. This one only has 1 significant digit. If I put a decimal point, boom, I would have 6, but there is no decimal point there, so therefore it's only 1 significant digit. These zeros' job are to push that 6 out. They're placeholder zeros. I could write this as 6 times 10 to the 1, 2, 3, 4, 5, and all those zeros disappear. Any number written in scientific notation given to you by the teachers will have only significant digits in it. So that is 4 significant digits. And again, if these zeros were not significant, this could go up to a 6, this could go down to a 4, and that is not what the experimenter is intending. They're intending 5.000, where this is my estimated digit. Do be careful though, your calculators will give you scientific notation sometimes. Not all of those digits are significant. It's the ones that we give you are considered significant. We'll address that more as the year goes on. So in this problem, these are trapped zeros, so they are significant. These are showing the degree of precision in which the instrument was used. If these zeros were not here, this could go up to a 5. This could go down to, start that again, could go down to a 3. The experimenter did not want that, so these 2 zeros show the degree of precision, and therefore they are considered significant. Same thing here. If this 0 wasn't here, this could be 1.41 or 1.39, but all those zeros are there. That last 0 is significant because it's my estimated digit, and therefore it is considered significant. Again, all digits written in scientific notation given to you by the teachers will be considered significant digits. 4 digits in this one because of the decimal point. So these zeros are trapped right there between this 2 and the decimal point. It makes them significant. It's not the same thing when we get numbers smaller than 1, 0.02 only has 1 significant digit. This 0 is not considered significant because all it does is push that 2 over. So I'm just going to go through these answers. Hopefully you did them on your own. You'll learn nothing if all you're doing is copying down the answers. So in this one, we had to round to the number in the parentheses, number of sig figs in the parentheses. So we need to write this number with 4 digits. We could simply put a decimal point there like we did, or we could write it in scientific notation. Both are fine. The key to these problems is to not change the number so much that it's a completely different number. So in this problem over here, number 19, we want to go to 2 significant digits. So we look at the 3rd significant digit. It's greater than a 5. So 0.005. And then we look to this 7. It's greater than a 5. So it's going to round that 5 up to a 6. Write that in scientific notation as well. All right, so we need to go to 3 significant digits, and a lot of you will do this. 180 or 180 dot. Would you like to get paid $1,800 for a week's worth of work? Or would you like to get $180 for a week's worth of work? You cannot change the idea of the number. You can round it a little bit, but the idea of the number, the value needs to be around this 1,800. The only way to do it is to write it in scientific notation. 21, we need 3 significant digits, so we look to the 4th. The 4th one is a 4. We don't care about this 933. So 11.5 is what our answer is. That 933 has no influence on our rounding there. Please try the next couple problems before you look at the answers. 2 significant digits. You don't want to change it to 18. Would you like to get paid $1,800 or would you like to get paid $18? Well, I would like to get paid $1,800. This is the only way to write it with 2 significant digits. Actually, no, you could also write it like this with 2 significant digits as well. Sorry about that. All right, 24 and 25. So our number is 1,800 and we can only have 1 Sig Fig. So we can go with 2,000, which has 1 Sig Fig. It's pretty close to 1,800. It's not exactly the number, but it's better to go with 2,000 than maybe 1,000. So if we're going to round, it's probably the 1,800 is much closer to our 2,000 value. We could write it just as this right here, 2 times 10 to the 3rd. That will convey it. So we are changing the number a little bit, but the idea of the number being around 1,800 is much closer if we have 2,000 than if we went with 1,000. Or if we just went with $2, which maybe some people would want to go. $2 is definitely not the same thing as $1,800. Okay? Or maybe $1. Maybe that's what some people put. All right, our next part is just about writing numbers in scientific notation, getting a little bit more practice with that. Make sure you pause the video, go through this entire part, and then I'll stop you in a little bit. Revealing answers as we're going. All those zeros are significant. This shows the degree of precision at which this instrument was used, so that 0 must be in there as well. These zeros are all significant. They are part of the measurement, so they must show up in the scientific notation. These zeros are part of the measurement. They show up in scientific notation. So again, numbers written correctly in scientific notation only contain digits that are significant. So these 2 zeros are not significant, therefore they did not show up in our scientific notation. And this is not one of your questions, so what I'd like you to do is the next page is your homework. So 85.2. Complete all of that. We'll go over that tomorrow. There are some answers at the very bottom of the sheet, so you can kind of check in to see if things are going well. I would definitely have my periodic table out with my Sig Fig rules on it. I would have my cover out of my unit pack in case I need to look at that to get a couple rules in my head. And come in for help if you need any assistance. Have a good day.